In this lecture, we're going to continue talking about convective heat transfer, and we're going to be working in Chapter 7. And Chapter 7 deals with a specific subset of geometries for convective heat transfer. And in Chapter 6, we talked a lot about boundary layers, a layer where a surface influenced a flow, both in terms of the velocity of the flow close to the surface, as well as the temperature of the flow close to the surface. So what's unique about the external flow that we're going to be dealing with in this chapter is that the surfaces that we're dealing with allow a boundary layer to grow unimpeded. So we can think about, for example, a flat plate. We talked about that before with reference to the last chapter, where the flat plate removes momentum from the flow, so it slows down the velocity, and the region where it has removed momentum from that flow and affected the velocity continues to grow as the distance from the leading edge of this flat plate increases. So as the flow continues over the plate, the boundary layer thickness increases, the velocity or the region in which the surface influences the velocity increases. And if we have nothing sitting above this plate, then that boundary layer can keep growing as far as it would like. And we're not limited to geometries such as flat plates. We might consider something like a cylinder as well. If a cylinder is introduced into a flow, then that flow stagnates at a point on the cylinder. You've studied this in fluid mechanics. And as we move around that cylinder, the flow has to change direction in order to navigate around this cylinder. And in doing so, the cylinder is going to remove momentum from that flow, so it's going to change the velocity of the flow. And likewise, just for the flat plate, just like for the flat plate, there will be a region in which this surface of the cylinder influences the flow, and that region can grow. And there's nothing stopping that region from, that boundary layer region from increasing in thickness. Now, we're going to split these two apart. I make a distinction between the two because the cylinder falls into a type of object that we might refer to as a bluff body. And what defines these objects as far as fluid mechanics is concerned is the fact that they tend to produce a wake. And we're familiar with this, for example, behind a boat. In water, we know that there's a turbulent region that follows this object follows this object in the flow, downstream of this object in the flow, where the shape of this object causes the boundary layer to separate from this object at some point and create a turbulent wake. And we'll discuss this in more detail later on. But this chapter in general is going to deal with all types of external flow where we allow the boundary layer to grow from the surface without impediment. So the goal of treating these geometries, we're interested in the heat transfer from them. So what we want to know in general is what is H, or what is the local heat transfer coefficient for a surface. In other words, if I had a surface at some temperature and a flow at some temperature, how much heat flux would I expect from a given point on that surface, or how much heat flux would I expect from the surface on average? So if I integrated all the heat fluxes over the surface and divided by the area, what heat flux would I expect on average for a given temperature difference? So basically, this is what we're going to try to find when we're looking at convective heat transfer problems. In the past, you dealt with convective heat transfer, you used Newton's law of cooling, but you were always given H. So now we're going to work on finding H. And how are we going to do that? Well, as we had considered in the last chapter, we could convince ourselves that by non-dimensionalizing the boundary layer equations, that we could find an expression that was exactly the gradient of the non-dimensionalized temperature with respect to the non-dimensionalized height at the surface. And so in our non-dimensionalized boundary layer equations, we had said that we could express the heat transfer or something related to the heat transfer in terms of this temperature gradient along with the thermal conductivity of the fluid. So this essentially gives us a non-dimensionalized form of the heat transfer coefficient. And this expression is termed as this term is called the Nusselt number. It's a dimensionless number, and we can think of it as a dimensionless form of the heat transfer coefficient. And so when we plugged into our non-dimensionalized boundary layer equations, we arrived at an expression for the Nusselt number as the heat transfer coefficient times some length scale. Now this is not, we need to consider the specific length scale that's appropriate for each problem, divided by the thermal conductivity, and importantly, that's the thermal conductivity of the fluid. Remember, we're interested in all of these in transport in the fluid phase. So the thermal conductivity that we're interested in here is the fluid. So if we can find an expression for the Nusselt number, then we can solve for H. And we furthermore convinced ourselves that the Nusselt number, at least the local Nusselt number, was a function of the non-dimensionalized position. So where we are along the surface, non-dimensionalized by some other length scale, and the properties of the flow, namely the Reynolds number, and properties of the fluid, which we could express as the Prandtl number. And this function, we don't know right now what it is, but that function is unique to a specific geometry and flow regime. And if we have a Nusselt number at any point on the surface, then we could integrate the heat transfer coefficient all over the surface, integrate the heat flux all over the surface, and then take the average of that, divide by the total area of the surface, and we could arrive at an expression for the average Nusselt number. And that average Nusselt number, now integrating over the entire surface, will no longer depend on the position and will just be a function of the condition of flow, the Reynolds number, and the properties of the fluid, the Prandtl number. So let's take a look at how this plays out in practice. So for example, we might ask a common question that we would probably need to answer in engineering. What's the local heat flux on a surface for a given condition? So for example, maybe we're interested in a flat plate, and you may wonder, I'm frequently drawing the flat plate with a sharp edge here. And technically, when we talk about these flat plate geometries, they really need to have a sharp edge that splits the flow at the leading edge. If they have a blunt edge, they're really more of a bluff body that we talked about before. And so to be technically accurate, those flat plates have a sharp edge. That's really a minor point, though. So let's consider this sharp-edged flat plate, and let's say that we measure it, and we know it's at a constant temperature, and we're asked to find out how much heat is leaving this plate, or let's consider more specifically how much heat is leaving this plate at a given position. And we know it's in a flow of fluid, let's say it's air, and that air has a certain velocity upstream of the plate. We can also call that U infinity here. In the flat plate case, later on we'll talk about there's a little bit of a complexity to that for the cylinder. But we know the velocity of the air, and we know the temperature of the air, and we know the temperature of the plate, and we know it's a flat plate. So we ought to be able to describe the heat that's leaving at a position X. We know that that's described by Newton's law of cooling. So if we knew what H was, then we could just say that the heat flux at that position is equal to H times Ts minus T infinity. So our goal in many heat transfer problems involving convection is to find out what H is for this case of interest. As we said before, if we can find the Nusselt number, we can find H. Now we're interested in a local position, single position of H. So we want the local heat transfer coefficient and the local Nusselt number. If we know Nusselt number, then we can say local H is just the thermal conductivity divided by the length scale. And since we're interested at a position of X, the obvious length scale that we're interested in here is the distance from the leading edge of the plate, or our position X. So we're going to calculate H as the Nusselt number times the thermal conductivity divided by X. And we know that the Nusselt number is a function of the local position and the Reynolds number and the Prandtl number. However, this local position doesn't even have to be explicit. And we'll see what we mean by that in just a second. So if we want to arrive at a value for the Nusselt number, well, we're given the velocity, the length scale, the temperature. We could look up the properties of air and we could find the Reynolds number, which would just be the velocity times the length scale of interest divided by the kinematic viscosity. And we could look up the Prandtl number, which is a property only of the fluid, and that's given by the kinematic viscosity divided by the thermal diffusivity. So if we knew what function this was, then we could calculate the Nusselt number and solve for H. So what do we need to know in order to calculate this function? Well, we know that this function is the solution to the boundary layer equations that we've written before. So if we were going to solve these differential equations, then we need to know the geometry. In this case, it's a flat plate. We need to know the flow conditions. In other words, is it laminar, is it turbulent, or is it in a transition region between the laminar and turbulent regimes? And we also need to know the heating conditions. For example, is this an isothermal plate? In other words, does the temperature stay the same? In this case, this is what we've specified, but we could also have other conditions. The other obvious one is perhaps we have a constant heat flux. So we have the heat flux the same everywhere, and in that case, we probably want to know what the temperature was, or the temperature difference between the surface and the free stream would be. One important thing I want to mention here is we've got to evaluate the properties of fluid at a location or at the situation that we're interested in. And so that's going to lead to an interesting question. Namely, these properties tend to depend, particularly viscosity depends very strongly on temperature of many fluids, particularly liquids. Things like engine oil and even water have viscosities that can vary dramatically over the temperature ranges of interest. So if we want to evaluate the Prandtl number, in reality, we probably should be evaluating this locally and integrating this as part of our solution. However, that's generally not practical, so we need to pick a temperature that we're going to evaluate these properties at. And that temperature can be different depending on what function we use for the Nusselt number, but usually what we're interested in is what's called the film temperature. And this temperature is halfway between the surface and the free stream temperature. So we need to know the geometry, we need to know the heating condition. We specified those for our example as a flat plate and an isothermal condition. And I'm going to plug in some numbers here. Let's say it's air flowing over this flat plate at 10 meters per second at a free stream temperature of 0 degrees Celsius. Let's say the surface is constant, it has a constant temperature of 100 degrees Celsius, and we want to know what the heat flux is at a certain position. Let's say it's 10 centimeters from the leading edge of that plate. So we've specified the geometry, we specified the heating condition, and now we need to think about what the flow condition is. And so the question that we want to ask ourselves is it laminar, or is it turbulent, or is it in between? Well, how do we answer that question? Well, we know from fluid mechanics we're going to look at the Reynolds number, the velocity times a length scale divided by the kinematic viscosity, or equivalently density times velocity times a length scale divided by dynamic viscosity. So here's the first case where we need to worry about what the properties of the fluid are. In order to evaluate the Reynolds number, we've specified the free stream velocity, and we've designated our length scale where we want to evaluate the Reynolds number. Now we want to know at this point, is this boundary layer laminar, or is it turbulent? Is there turbulent mixing? Well, that's going to depend on what the Reynolds number is at this point, as defined by the free stream velocity times the distance from the leading edge to that point divided by the kinematic viscosity. In order to evaluate that, we need to evaluate kinematic viscosity nu, and that depends for certain fluids very strongly on temperature. Actually, it turns out for air it's not so sensitive. But for example, at room temperature, it could still double over a range of, for example, 150 degrees C. If I went from 300 Kelvin to 450 Kelvin, my kinematic viscosity would almost be 2 times as large. We can find for liquids, almost invariably, well, at least most commonly, liquids' kinematic viscosity decreases with temperature, and those decreases can be extremely large, orders of magnitude. And you can kind of think about this from your everyday experience. You've probably seen engine oil or grease or something that's, when it's cold, is extremely viscous, or honey, for example. But if it's warmed up by not that many degrees, its viscosity can thin greatly. So again, we need to decide what temperature we want to use to evaluate the kinematic viscosity. Well, as we said before, that temperature is going to be somewhere between the free stream temperature and the surface temperature. And so usually we use the film temperature, this TF or T film, which is the average between the free stream and the surface. So in our case, it's the average between 100, 0, or it's 50 degrees Celsius. But that's not always the case. So what I want to caution you is always check the correlation that you're using. And we're going to define what we mean by the correlation. In other words, this is the function that defines Reynolds number, defines Nusselt number in terms of Reynolds number and Prandtl number. And each correlation will tell you what conditions it's valid for. So be sure and check that they intend for you to use the film temperature. But this is the most common choice. Okay, so at that film temperature of 50 degrees Celsius, we can go look up in a table and find that the kinematic viscosity is about 1.8 e to the minus 5 meters squared per second. And the table for, and again, this is for air, we have to obviously specify what the composition of the fluid that we're dealing with is. And this table that you can look in your book, probably not on that page number in the book, this is probably from an older edition, but I believe it's still table A4, has thermophysical properties of gases at atmospheric pressure. You likewise have properties of liquids in another table. And so this is for air. The table goes on to list other gases. Here's ammonia. But the table will give you all of the properties that you need to evaluate the heat transfer coefficient, as well as some other very useful ones for later. So in this case, we're interested in the kinematic viscosity nu. Now, one thing I want to point out to you, and let's see if I can maybe zoom in a little bit on this, make it a little clearer. And this table from your book expresses the quantities in a specific way that I want to be sure and point out, because sometimes I think it's a little confusing. Namely, you see they write the viscosity as dynamic viscosity times 10 to the 6th, and then they have a number here, for example, of 2. So it's important to note that the quantity 2 is equal to nu times 1 million. In other words, nu at temperature of 100 degrees Kelvin, or 100 Kelvin, is equal to 2 e to the minus 6, or 2 times 10 to the minus 6 meters squared per second. So be sure and note, if you see tables that use this sort of nomenclature or way of reporting the values, if they say the variable times a number, then that is the value that they're reporting there. So if you want the value of the variable itself, we need to work out the math and say that this is equal to the value reported. So the variable itself is equal to the value reported divided by this multiplier. Okay, so I just wanted to clarify that in the table. Other tables you may see won't use this. They'll actually just report this as 2 e to the minus 6, or another way you may see this reported is in a table that has a heading that would be something like nu, and then in units they might say 10 to the minus 6 meters squared per second. And now this table likewise might say 2, and it would mean the same thing, but we have to distinguish between this 10 to the 6th multiplied by nu and a unit that might have some multiplier in it. So table 8.4 gives you the properties for air, for example, for this problem. Okay, so now that we've found the kinematic viscosity, then we can evaluate the Reynolds number. And the Reynolds number is just the free stream velocity times the position, which is our length scale, divided by the kinematic viscosity. If we plug in the value for the film temperature for kinematic viscosity, we get a value for Reynolds number of 56,000, about 5.5 e to the 4. Okay, so what are we going to do with that Reynolds number? Well, the first thing, that Reynolds number really, well, we know physically it tells us the effective inertia over viscosity, or inertial forces to viscous forces. So it tells us about the flow, and the first thing we're interested in is that flow laminar or turbulent? Well, how do we determine that? Well, we compare the Reynolds number, again, at that specific position. That's at position X. That's why we use the little subscript. We're going to use the subscript to designate the length scale that we're using for the Reynolds number. We compare that to the critical Reynolds number. There is some Reynolds number above which the inertia is sufficient that it's going to overcome the tendency of the viscosity to damp out perturbations. And if the Reynolds number is high enough, the inertia is high enough, those perturbations will cause mixing in the flow. They will allow a perturbation to carry the momentum of the fluid so that it pushes another element of fluid away or out of its way and creates mixing. So the key point here is that at some critical Reynolds number, we would expect to transition from laminar to turbulent, just as you discussed in fluid mechanics. Well, this critical Reynolds number, of course, depends on the geometry. For a flat plate, that critical Reynolds number is about 5 times 10 to the 5th. In reality, it can vary with roughness of the plate and other conditions of the flow, but your book uses a single number of about 5e to the 5th, and that's good. It may vary by maybe a factor of 2, a factor of even 5 on either side of that, but this is a good number to use. So in our case, we're well less than that. We're about 5e to the 4th, so we're about 10 times lower than this critical value. So we're definitely in the laminar regime. Okay, so we've defined the geometry, we've defined what the flow condition is, it's laminar. Now we need the Prandtl number. The Prandtl number, again, function of temperature. For a gas, it varies only slightly. For ideal gases, it's not a strong function of temperature. However, for liquids, it will tend to be a very strong function of temperature because, again, the Prandtl number is kinematic viscosity over the diffusivity, thermal diffusivity. And so we know kinematic viscosity varies a lot with temperature. So Prandtl number can vary very strongly. Some just very rough numbers for Prandtl number for air, for ideal gases, they're usually on the order of 1. For air, it's about 0.7. For water as a liquid, it actually varies quite a bit because of the kinematic viscosity, but at room temperature, 300 K, it's maybe around 5, but it can vary very quickly. The viscosity of water changes by about 2% per Kelvin around room temperature, so this can change quite quickly. For oil, it's much, much greater than 1 because the viscosity is large compared to the thermal conductivity. On the other hand, for liquid metals, Prandtl number is much, much less than 1. Liquid metals have a very high thermal diffusivity, good thermal conductivity, but they don't have a viscosity that's that much different than water or than water. So the Prandtl number that results is much, much less than 1. Okay, so we've now got everything that we need to evaluate that function. We know it's that the function describing the Nusselt number depends on the Reynolds number, the Prandtl number, potentially on the position, but there's nothing stopping us from having a function that is just equal to a constant value. So in this case, our Nusselt number, our local Nusselt number, is just a function of the Reynolds and Prandtl number. So we said in general we were looking for something that looked like a function of position, Reynolds number, and Prandtl number. And once we knew what this function was, we could evaluate the Nusselt number. In order to know what this function is, we needed to figure out the geometry, the flow condition, the heating condition. We've done that, and then that allows us to go look up what the function that we want to evaluate for Nusselt number is. In our case, this function happens to be equation 723 in your book, and we'll talk about how we can arrive at these functions in a later lecture. But as a good rule, or not really a rule, but a practical avenue, the practical reality is that we're going to look up what these functions are. We're going to have a table where someone has compiled, usually experimental data, to provide us with these functions for Nusselt number. You did that in one of your laboratories. You calculated a Nusselt number from experimental data. Well, people have done that for a very large number of experiments and come up with these functions for us. So for this flat plate that's in a laminar flow regime and isothermal, we can apply a function that looks like this, where the local Nusselt number is equal to a constant times Reynolds number to the 1/2 power times Prandtl number to the 1/3. Now, this, what would be termed a correlation, when we talk about correlations for Nusselt number, this is what we're looking at. We're looking for a function of the Nusselt number in terms of the Reynolds number and Prandtl number. And each correlation will have certain limitations on it, the conditions for which it's valid. So in this case, we're interested, or this is valid for a flat plate in laminar flow and isothermal heating, but it's also limited to Prandtl numbers. and namely it needs a Prandtl number that's larger than about 0.6. So for large Prandtl numbers, for water, for air it's okay, for water it's good, for oil it's good. It would not be a good solution for liquid metals. Okay, so now we've gotten this expression, so we're halfway there, more than halfway there. Now we can plug in what we've evaluated in terms of the Reynolds number and the Prandtl number and solve for a Nusselt number. If we plug in these values for a Reynolds number, 5e to the 4th, Prandtl number about 0.7. Again, we get this from the same table of properties for air. We can either, if they don't give us the Prandtl number exactly, which in this table they do, they give you Prandtl number explicitly, but they'll always at least give you the thermal diffusivity or maybe the thermal conductivity and the specific heat and the kinematic viscosity. So from that combination, we can always calculate the Prandtl number. So we look that up for our film temperature, and we find a value of 0.7. We plug that in, and we arrive at a Nusselt number of 70. And so this is, we've covered the major hurdles that we need to in order to evaluate the heat flux, because now we got the Nusselt number, we can evaluate a heat transfer coefficient, and we can find the heat flux. And I want to point out that this correlation, along with many others, shows up in table 7.7 at the end of chapter 7. And both chapter 7 and chapter 8, I encourage you to immediately flip to the back of the chapter and look at the summary and the tables, because it will list out all of the correlations that are covered in those chapters. Okay, so we've solved for a Nusselt number at relevant or accurate at position X, valid at position X. And so now to solve for the heat transfer coefficient, we just need to multiply that Nusselt number times the thermal conductivity and divide by the length scale, which in this case is just X. Again, at the film temperature, we can evaluate the thermal conductivity of the fluid. Importantly, this is for the fluid, not for the surface. And we find that for air, it's about 0.027 watts per meter Kelvin. So we can plug in the Nusselt number we found, 70, the thermal conductivity, and divide by the length scale. And we're going to come up with a heat transfer coefficient of about 19 watts per meter squared per Kelvin. Specifically, that's the local H. Remember, that's at a position of X equal to 0.1. This is 0.1, 10 centimeters from the leading edge of our plate. So once we have the heat transfer coefficient, we wanted to find the heat flux. So we're just going to take that heat transfer coefficient, again local at this specific position, multiply it by the temperature difference between the surface and the free stream, and arrive at a heat flux. In our case, this would just be about 19 times 100 or 1,900 watts per meter squared. Now, importantly, that was the local heat transfer coefficient. So we were able to answer what is the heat flux at a specific point. On the other hand, if I'd ask you how much heat was the plate losing over that entire length, what was the heat rate, how many watts were being dissipated by that entire plate, then you would need to evaluate that heat transfer at all points in the plate and add them up, integrate that heat flux over the plate. Or alternatively, or actually synonymously, we could define an average heat transfer coefficient. So we said the heat flux locally was equal to the heat transfer coefficient times the local temperature difference. Likewise, we could say that the heat rate globally was equal to the average heat transfer coefficient times the area times the surface temperature of the plate minus T infinity. Now, probably this only makes sense if the surface temperature is uniform, so if there's no variation with X. But oftentimes we're interested in this average heat transfer coefficient, which we're going to specify as h bar. So the bar over the top in general we'll use to designate an average quantity. Well, to find the local heat transfer coefficient, we related it to a local Nusselt number. To find the average heat transfer coefficient, we can also relate it to an average Nusselt number. And just a reminder, we talked about this in the previous chapter, our average heat transfer coefficient we can get from integrating this heat flux over area and then dividing by both sides by the temperature difference. And so we would get that the average heat transfer coefficient was equal to 1 divided by the area times the integral of the heat transfer coefficient over the area. Or for a flat plate where we don't care about the width, or there's no variation of the properties across the width of the plate, then we could also express this as h bar equal to 1 over x times the integral from 0 to x of h dx. And specifically, this would be the integration between the leading edge and whatever our position x was. So we could say, for example, now if I ask you what is the total heat rate, what's the total heat lost over the length x, then we would say that heat rate is equal to the integral of the heat flux over this length over A. And we could define h bar again as the total heat rate divided by A times the temperature difference, or 1 over A times the integral of h bar dA, or h dA. So let's look at the specific case then for the flat plate in laminar flow with isothermal heating. Well, our local heat transfer coefficient, again, always just the Nusselt number times the thermal conductivity divided by the length scale. And we have a specific form now for this Nusselt number. For this laminar flat plate, our Nusselt number had the form of local Nusselt number being 0.332 times the Reynolds number to the 1/2 times Prandtl number to the 1/3. So I can plug in this function for Nusselt number, and I can integrate the local heat transfer coefficient over x and divide by 1 over x, and I would arrive at an expression for the average heat transfer coefficient that would look like this. So I have my prefactor, my coefficient, times Prandtl number to the 1/3. The Reynolds number varies with x. This is Reynolds number as a function of x, so I have to include that in the integral. And I've divided by x. So this is Nusselt number times kf over x. So kf is here. This is the x from here. This x corresponds to my normalization. I've got to divide by x so that I end up with a quantity that is has the same units as a heat transfer coefficient. I'm integrating over x and then I'm dividing by x out here. So that's where that one's coming from. Okay, so if we integrate the Reynolds number to the 1/2 divided by x, well, Reynolds number is the velocity divided by the kinematic viscosity times x. So maybe let's go ahead and expand this real quick. We would say that this is equal to viscosity times x, all raised to the 1/2 power, divided by nu to the 1/2 power, and then that's all divided by x. So if we expand that, we can pull out velocity over kinematic viscosity to the 1/2 power, and we've got x to the 1/2 divided by, or the 1/2 power divided by x, or just 1 over x to the 1/2 power. And so this is the integral from 0 to x of x to the minus 1/2 times dx, or just 2x to the 1/2 power. So if we reorganize that a little bit, we get that h bar is kf over x times this coefficient, Prandtl to the 1/3, ratio of velocity to kinematic viscosity to the 1/2 times 2x to the 1/2. Or if we group these back together, we get again the Reynolds number to the 1/2, and we just pull a factor of 2 out, and our prefactor becomes twice as large. So basically we just find that the average heat transfer coefficient over length x is just 2 times the local heat transfer coefficient at that end. So in other words, if we had a flat plate, and we were interested in the average heat transfer coefficient over the distance between the leading edge and the position x, then that average heat transfer coefficient is twice the local heat transfer coefficient here. And that makes sense because we know the boundary layer is growing from the front leading edge to the position x, and as that boundary layer grows, then the temperature gradient is decreasing. This boundary layer, at least the thermal boundary layer, is telling us the distance over which heat has to diffuse to reach a temperature, the free stream temperature. So as this distance increases, we would expect the rate of diffusion to decrease because our gradient is getting smaller. Right near the leading edge of the plate, we have a very large temperature gradient because we have free stream temperature very close to the surface of the plate, and so we get a very high heat flux. And if we integrate over this, so the heat transfer coefficient is larger near the leading edge and decreases as we get farther from it. If we integrate over it, we expect to get a heat transfer coefficient that is larger than the heat transfer coefficient at the end. And for the laminar flat plate, that's exactly 2 times. So likewise, the Nusselt number, the average Nusselt number, would be the average heat transfer coefficient times x over the thermal conductivity. That would be equal to 2 times the local heat transfer coefficient times x over the thermal conductivity, or 2 times the local Nusselt number. But this is only specifically true for this specific case where the Reynolds number or the Nusselt number is proportional to the Reynolds number to the 1/2, and so that when we integrate it, that results in a recovery of, or integrate it divided by x ends up in a recovery of Reynolds number to the 1/2. So this specific relation only true for this specific case. But in general, we can always apply the integration of the heat transfer coefficient to obtain the local heat transfer coefficient to obtain an average heat transfer coefficient. And we can apply the same calculation to obtain an average Nusselt number.